Sake, it's one of our other monkeys, typing on a keyboard. Now, this is telepathic typing. So to be clear, this is he's not actually using a keyboard. He's moving the cursor with his mind to the highlighted key. Now technically, we can't actually spell, and so I don't want to oversell this thing. But what's really cool here is Sake the monkey is moving the mouse cursor using just his mind, moving the cursor around to the highlighted key, and then spelling out what we want to spell. But and then so this is something that could be used for somebody who's say quadriplegic or tetraplegic human, even before we make the spinal cord stuff work, is being able to control a mouse cursor, control a phone, and we're confident that someone who has basically no other interface to the outside world would be able to control their phone better than someone who has working hands. I think it's also important to show that Sake actually likes doing the demo and is not like strapped to the chair or anything. So So the monkeys actually enjoy doing the demos because they get the banana smoothie, and it's kind of a fun game. So I guess the point I'm trying to make is like we care a great deal about animal welfare, and I'm pretty sure like our monkeys are pretty happy, you know. So as you can see, a quick decision maker on the fruit front. So for the first two applications we're going to aim for in humans are restoring vision, and I think this is like notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision.
We can stimulate neural activity in the brain by injecting current through every channel. This is important because it allows us to bypass the eye and generate a visual image in the brain directly. In this image, I've highlighted the calcarine sulcus in red in an MRI. It contains a map of the visual world, the visual field. It's about a surface area equal to a credit card on each side. One of the seminal discoveries was that every cell in the visual cortex represents only a tiny part of the visual field. Your perception is made up of a mosaic of tiny receptive fields, each belonging to a single cell in your visual cortex. So if you record from one of these cells in a monkey, say in this location, you can find a very tiny region of the screen where a light stimulus will cause modulation of that neuron. This is a schematic of what a visual prosthesis using our N1 device might look like. A camera, the output from a camera would be processed by an iPhone, for example, which would then stream the data to the device, and the image would be converted into a pattern of stimulation of the electrodes into visual cortex. With 1,000 electrodes, we might be able to produce an image resembling something that you see there on the right.
So our first steps along these dimensions for our device is what we call the N1 implant. It's a size of about a quarter, and it has over 1,000 channels that are capable of recording and stimulating. It's microfabricated on a flexible thin film arrays that we call threads. It's fully implantable and wireless, so no wires, and after the surgery, the implant is under the skin and it is invisible. It also has a battery that you can charge wirelessly, and you can use it at home. For implanting our device safely into the brain, we built a surgical robot that we call the R1 robot. It's capable of maneuvering these tiny threads that are only on the order of a few red blood cells wide, and inserting them reliably into a moving brain while avoiding vasculature. So here it is. That's our R1 robot with our patient Alpha, who's lying comfortably on the patient bed. This is what we call the targeting view. So what you're seeing is this is a picture of our brain proxy, And the pink represents the cortical surface that we want to insert our electrodes into, and the black represents the vasculatures that we want to avoid. So this is another view, real quick. On the left is the view of the insertion area, and on the right, what the robot's going to do is it's going to peel the array, the threads, one by one from its silicon backing, and insert it into the targets that we predetermined in the targeting view.